Okay, so here are the properties of solids, and solids will have a few similarities to liquids in the fact that they will have a definite volume, so they'll kind of take up the volume of a container that they're in. Now, a liquid will, if you move it, will obviously flow to various places, so it won't keep that volume for long if it's moved or spilled, but while it's in a container, it will maintain a definite volume. Now, solids are a little bit different in the sense of their shape. They have a definite shape. Solids do not flow. They don't move around in that sense like a liquid would or like a gas particle would. They hold their shape. That's because we have very strong, again, attractive forces between particles. So typically the larger your particles, the closer each of the atoms are to each other, the more attracted they are. And this draws them closer together, and that allows them to have a fixed volume and a fixed shape, which then defines them kind of to be a solid. Now, this is the reason why we can have solids at room temperature, liquids at room temperature, and gases. It all depends on the attractive forces that are present. So within certain gases, we know a lot of gases will typically be kind of like, we could have chlorine gas, oxygen gas, nitrogen gas, one element bonded to itself. And that will allow kind of not really any attractive forces between the particles, since there isn't really a polar bond between the two molecules, and they can't, when they're bumping into each other, they don't really care because they're not attracted to each other because they're the same thing. So gases don't have those things. So if you have certain elements that don't have those attractive forces, they're more likely to be a gas at room temperature. If you have for example, water is typically liquid at room temperature because there's a little bit more attraction between particles. As that attraction gets stronger, we work our way up to solids. So, for example, sodium chloride is a solid at room temperature, table salt, sodium, and chlorine together, and they have a very strong bond. They have an ionic bond, which is very, very strong, and they have kind of positive, the sodium is usually a positive ion, the chlorines are usually negative, and when they arrange themselves, they're in a fixed shape because of the strong positive and negative attractive forces present. Thus, we get a solid at room temperature. So based on your attraction forces, that'll determine if you're a solid, liquid, or gas. Now, solids have limited movement between their particles. The particles, the individual atoms, are typically in a fixed location. They don't move, they have a certain structure, and that is it. So, unlike a gas and a liquid where there is some movement, gases have a lot of movement, liquids are a little more restricted, solids are even more restricted, and they're basically fixed in the spots that they're in. So when we get those fixed spots, we kind of get a pattern. So we'll have an ordered arrangement between my different particles. So I usually get a lot of times a repetitive pattern between each of the elements, the way that they're laid out, because they can't really move. So as soon as they pick a spot, and they're kind of like locked in, so then you get this repetitive pattern based on that. Now, solids are very dense because we have particles that are very, very attracted to each other. So they're very close. They're larger particles, so since they're closer together and heavier typically, that makes them more dense. So they have less volume and more mass. Again, density is based on mass and volume of certain objects. So when I think about density, and if I have a solid, solids again have a fixed volume. If I take and put some pressure on a solid, a lot of times the volume itself won't change. If I put pressure on a gas, I can compress the particles closer together with a lot of pressure, thus decreasing the volume. I can do the same with liquids, not as much as a gas, but there's still some wiggle room. Solids, if I push them together, a lot of times they'll just shatter. So a lot of times when you put pressure on a solid, like for example sodium chloride or table salt, you're kind of pushing together the positive parts of the compound, and you're pushing them next to other positive parts, which positive and positive repel each other. Same thing with negatives being pushed close together. So a lot of times the solid will just shatter and break. So you haven't really lost any volume. You still have all of the pieces. You still have all of the original starting pieces. They're just in multiple pieces versus one solid chunk. So pressure, and as far as being able to compress a solid, at room temperature you can't really do unless you heat it up, melt it, those types of things. So there's two types of solids, and there are some different arrangements as far as names and stuff. Basically what I want you to know is that there are crystalline solids and then amorphous solids. The first type is crystalline solids, which you probably obviously have had some experience with. Table salt is a crystal. Those types of things. So when we have a crystalline solid, we have a predictable ordered arrangement. So it's a repeating unit over and over and over. And I get kind of a 3D geometric shape because everything is fixed, and since it repeats and I can predict the order, I can kind of predict and I will see a shape. So a lot of times in geology, and when we study different crystals and rocks and stuff, we'll see these crystalline solids. So for example here, this would be like a cubic solid, so I can see the repeating unit is in the shape of a square or a cube. This face is a square. This right here would be a hexagonal unit, and I know it's a little hard to see here, but basically you've got a hexagon type structure, okay, that repeats, and this is kind of another example of that. So you get these repeating 3D shapes throughout your crystalline solid. Now, the other type of solid I can have is amorphous, and amorphous just means that I don't have a predictable arrangement, and thus I don't have like those pretty 3D shapes. So a lot of times I'll have this kind of pattern in glass and rubber and plastics. They're kind of just these long chains strung together, long chains of molecules put together in rubber and plastics, and that doesn't give me any kind of repeating definite shape. It's just kind of a blob, so to speak, of stuff that's hooked together and is really attracted to each other because it's a solid. It's just not repetitive and nice and neat. So here you can see this would be an example of an amorphous solid, and this would be an example of a crystalline solid. So here I can see I've got a definite repeating pattern between these little triangles, the overall structure. This not so much. I mean, I can tell the different types of elements I've got, but they're kind of all over and locked into their spots the way that they are. If I have a certain type of like liquid or a melted version of a certain type of crystal or rubber, those types of things, if I cool it really fast, the molecules are kind of just forced to stay where they're at when they're cooled, so I don't really get a real good repetitive pattern. I don't get real good crystals. So if I cool certain things real slow, it gives the molecules time to kind of sit where they want. When it's fast cooling, they're kind of just, it's like a shock effect, and they're just kind of stuck where they are, and then they cool and stick, and they're in that fixed shape. So sometimes it'll look a little bit more messed up. So if you cool something really fast, you typically will get more of a structure like an amorphous solid instead of a crystalline structure. Okay, here's what we're going to do next. Hopefully we have enough time. We're going to take the sub has got some statements for you. They're true-false statements, so you're going to work with your seated partner will be fine. You're going to go back to a lab station, so you've got a little bit more room to organize all your statements. Organize the statements in true and false categories, and so just 2 columns, sort them out quickly. You're going to then, once you're sorted and everybody in your lab bench, so at your lab table is sorted out, go ahead and take a look at what they've got and what you have, and kind of discuss with them some of the differences or why maybe they put what they did and you put what you did. So if you have some false statements that maybe are in a true category for somebody else, discuss that with them. And then the teacher or the substitute here will have the correct answers to go over with you. So make sure you take note of what those are. When you're finished with that and everyone's all set, we can go back to our seats. What I would like you to do, just like we did for the gases, I'd like you to do a mind map for liquids and solids. And again, the mind map has a central idea in the middle, so you have liquids and then kind of branch off your different properties. If you'd like to color code it, there are some colored pencils. Make sure you include some graphics with each of the things that you write down, so you kind of have a visual of what those meant and how those relate. So a separate one for liquids, a separate one for solids, and keep that in your binder so you can keep that as part of your notes. I'll be checking those when I come back. One other thing for your homework, so once you're done with the true false and you've worked on the mind mapping a little bit, I have a few questions on a worksheet for you to answer. So go ahead, if you have time, you can work on them in class, obviously. If not, if you'd like to work on the questions before you leave class and save the mind mapping for home, I don't care. Pick one or the other to work on. Either way, we'll be checking them and going over that stuff on Monday when I get back. So, if you have any questions or concerns, shoot me an email, post a Skyward message if there's anything that doesn't make sense or is unclear in any way, and I will see you on Monday.